Okay. Hello, everyone. Welcome back. So today we'll continue on the project presentation. So we have two teams for today, right? And here's the first team, Jesus and Karen. And Jesus will present a forecast of stock value by discrete time Markov chain modeling. Okay, so I'm going to hand it over to Jesus. Thank you.
Okay, so hello everyone. So my name is Jesus. I'm presenting this project about stock forecasting. But now let's first begin with what is a stock and what is the stock market. So as introduction, the stock market is the place where companies trade and sell part of the company in exchange of some funds to investors or institutions. So this part of the company is called shares, and they are kind of like little pieces of the company ownership. Once these initial shares of the company have been sold, so the investors that obtain that shares, they can sell it to another person or another institution, and that's why whenever you begin to trade in stocks to other person, and the value of this stock begin to change. For this reason, so it is very important that whenever you buy some stock and then you want to sell it, so you want to sell it higher than whenever had you got it. However, if you sell it lower than you got it, you will lose money. So that's for this reason it's very important to predict the stock value or the trend that the stock is gonna follow in order to make some profit, or more important, not to lose all the money. So, how's the problem? The problem statement in this forecasting is that the market is changed very randomly. There's several factors that affect the stock price of some company stocks, and also the market in general. And moreover, this doesn't discourage researchers to develop models that can give us a hint of where the market is going. So, his research question for this project was if the Markov change can be implemented to predict stock value, and can this represent any profit based on these predictions for an investor. So as a background, so we utilize Markov change. That we know that it's a process that changes from one stage to another, and has different probability of transition. And also this is used to describe random variables, and we know that the stock market is has a lot of randomness in its behavior. So as a background, so I found some research that are related with this one. One of these was done by Doubleday and Insurance. They utilize the stock prices, the stock closing price. And additional, so they basically what they do is utilize the stock closing price of the Dow Jones, and then they create different stages based on the value of the stock price, and then kind of like an intervals. And they use, for example, they use three at the beginning. They use high, medium, and low, and then they use very high, very high, medium, very low, and low. And they also can compute the long-run behavior, and then they see where the market is going. If there's more probability to go to the higher stages, so then it's going to be an increase of the market value. There's also more complex models that they use also Markov change, but what they do, they combine different factors. So they create a state of different factors combining, like if the volume is high today, and then the highest price or average price, so they kind of combine different factors in a same stage, and they create like very various stage. They create like 10 or more. And there's also some machine learning research that they do is they change the state depending of the stock. So it's basically trying different states until they find some optimization of the state formatting. But what I did is basically kind of like the first one, but I also generate state different for each stock, but I'm going to talk a little bit about that. But for model formulation, so first we need to define 4 things: the variable that we are using, that we are analyzing, the states that we are using for our analysis, and the step that is going to take for transition. Since it's going to be a discrete time microchange, it's going to be 1 day, 1 market day. I mean, because weekends the market is not open, so it's going to be 1 market day. And we also need to estimate the transition probabilities. So first, the variable. So whenever you get information from a stock, you get 5 things: open price, closing price, volume, high price, and low price. So for this project, I decided to utilize the close price because it's whenever our transition ends. So it's 1 day to another. So the close price will be the end of the day. I also decided to utilize volume because there's a correlation in the volume and the price that is selling the stock. So if you have a lot of the volume is basically the amount of transactions that you have every day. So if you have a lot of demand, the price will go down, but it's not really going. The value of the company is not really going down. It's just that there's a lot of transactions, and if vice versa. So that's what I decided to correct for the volume, to see basically the real behavior of the company, not the apparent behavior between if there's a high demand or low demand. So the formula that I utilize is this one. So basically I estimate the percentage of change between 1 day to the other. So I use the closing value and the closing value of the previous one, and then I divide it by the closing value. So this will give me how much the stock increased from day 1 to day 2, and so on. And I also multiply it by the mean of the volume, divide by the current volume, because it's the inverse. So if you have high demand, you will lower the price, and if you have low demand, you will increase the price. So that's basically is telling us if the volume was high or low in that day. Compared with the mean of the volume of all the samples, and you can see in this plot So this is basically one sample that I take. It's 120 days, and you'll see that the values are basically around 4.5 and minus 4.5. So that's the maximum change of the stock price between 1 day to another. Now let's continue. Okay, so has a state definition. So then, since I was using the percentage, and then I saw that most of the stock were basically between 4 or minus 4% of increase. Moreover, whenever I try to do a fixed state, so some of the samples doesn't get until the very high values, or they even have smaller values, so they even have higher values, and you can count and those in the state of the system. So that's why I decided to use better a variable state based on the sample characteristics. So these are some of the results that I used for fixed state, but I couldn't get any good data from that. So basically, what I did is measure the maximum and the minimum. So here's the maximum and the minimum, and then divide this between 5. So I create 5 stages, and I divide it in the same size stages. So as you can see here, so these are the 5 states, and then so the first one is going to be very high, and it's going to be our maximum value minus our cape value. Our cape value is basically this size. It's going to be this is going to be the K value. It's basically the size of each state. So it's going to be like an interval. So these are the limits of the state. And then you can see I define 5 stages and states. And the neutral state will be basically the mean of the state of the percentage change. And then these are going to be opposite, and then these two are going to be opposite. Here's the formula to estimate K. It's basically higher minus the lowest, and loss will be the negative one, and then divide by the number of states. So then, after I have the state definition, so I decided to compute for the sample the different state transitions that we have. So for example, let's say this one is a state 1, and then next day it will go to state 4. So then we have, it was a state 1, and then next day it will go to state 4. So I did that for all the samples that we have, so, one day to another, the change of stages, and then I count all the transitions that we have. And if, like this, we have three transitions. So we visit the state 1 3 times, and then we change to another. So then the probability from going to stage 1 to the other will be basically dividing all these 3 by the sum of all the row of the matrix, and then we get the transition probability matrix. So we basically see how many times we visit that state, and then if we are in that state, how many times we go to state 2, state 3, and state 4, and then we just divide that over the total, and we know the probability. Okay, so then we compute the probability transition matrix. That this also will help us to predict a little bit the market. So let's say we saw some increase of 5%, and then one day, and then so we know that according to historical data and the probability, we will go lower the next day. So then if we here we want to get out, so this is the good time to get out of the stock and sell the stock with a higher price, because the next day we are gonna go down. The same here, if you go down, so the probability says that it's probably go down. Only 9% will tell us that we are going to lower more. So then we can just buy some stock, and then we will increase the value. Okay. So now for the sampling of the data, so I decide to take different samples of different days, so 30, 60, 120, 180, and 360 days, which is basically 1 year. So basically what it is to write a program, and it will basically extract the data and estimate the transition probability from all the data that I have, and then generate a prediction. Moreover, since the limit time, I couldn't find any good way to compare between the different samples, and I decided to use 180 days. Also, the days were consecutive, so the sampling were 180 days before the day of the forecast. And now the prediction. So we can use the Markov chain to predict some things, and what we are going to do is to calculate the steady state transition probabilities, which is going to be the long run behavior of our system. So we will be able to describe the future by using these pi values that we are going to estimate. So first, and also we are going to multiply these pi values by the mean value of each state, because there's several values of each state. So the mean value will be the middle one, the average of the limit of the two limits. We calculate these mean values by this one. Okay. So that's basically just the average of each state. And then to calculate the long run prediction, so we are gonna elevate to the power of an infinite number, and we are gonna get our pi value. So I saw the long run behavior. You reach the long run steady state of the matrix around 5 days, and then you compute the pi values and you multiply it by the mean value of every state, and then you get the amount is the percentage, the daily percentage change of the stock in average on the long run behavior. So if we know how much it's gonna in the future how much it's gonna increment the stock in average, so we can know the price based on the current price, and then times the increment, we will get a trend of the stock, as you can see here. So basically this is gonna be alpha, which is gonna be our slope, and then the average daily percentage change is going to be, like I said, the multiplication and the sum of the pi values times the mean value of each state. We have our initial point, which is our current price, and times the percentage change plus the current price times the current stock price. Will have the slope of the prediction, and since it's going to be linear, as you can see here. And the independent variable is going to be the days that we are in the future. And so that's going to be pretty much it for the prediction. And now what I want to do is to validate if the results were going to be, so for the second question, if the results are going to be good to predict the price of the stock. So I decided to take a sample of several companies. I utilized 10 companies. So as you can see, there's different categories of the companies. So I decided to use very high companies as well as very low companies in terms of market capital, which is basically the amount of money that they have in the stock market. Also, if they lose money last year or they gain money, and the volatility, which is basically how it behaves between the markets. So if the market rise and then the stock will rise the same as the market, it will be a volatility of 1. If it is higher, then whenever the stock rises, you will have higher increment, or as well as if it decreases, you will have lower. It will decrease more than the overall market. So these are the stocks that I select, and then I also use different role of the company. So then we generate 5 plots for each stock. So there was a total of this is now 50. So we generate 50 plots of the market compared with the historical results. So basically we take 1 day and then we predict from the past of those dates, but we already know the future since it's a past date. And these samples were taken 5 years before today. Before the 1st of January, 20th of January. Let's see. So I made 3 parts of the analysis. So the first one was to see if you predict at 20 days, 40 days, and 60 days, you predict an increment. And so if you predict a positive percentage change, and then if the stock value is indeed 20 days after the day of sampling or increase, that's a good one. So if 40 days after the day of sampling increase, that's also another one, and 60 days after the day of sampling increase, so that's another one. So I basically count 3 of good predictions. So as you can see here, so there's no any good one because all the three aim days were lower than the predicted, and in this one, all of these were lower, and also we predict some lower values. So then we get to get a good prediction. So these are basically the results. So this is telling us that for a 40 days prediction, for the 5 plots that we get, all of them predict the gain of the loss of the stock. For example, for this one, only one predict the gain of the loss of the stock over that span of time. But we still get a really good results, which is 66% for 20 days, 64 and 64 for 60 days. So this is good because we know that if we invest 10 times, 6 of them we are going to have the right prediction. So we are basically gaining in 6 of them and losing in 4 of them. So if we basically gain and lose the same amount, we will gain over 2 of them, which is good. It's a good. I consider that it's a good prediction for investing. And then for the second part, I count how many times the line crossed the real value. So basically, how many times we predict the SAC value. So we found that only 40% of the times the prediction wasn't exactly accurate, and actually 46% of the time we predict the value over the future more than 3 times over the 60 days. that we predict. So that's also good because you know that whenever you have a price and then you predict certain price, you know that if the stock is going down, so there's a high probability that it's going to match your prediction, because there's a probability of 76% that the stock value is going to match your prediction. So if you predict an increase and then you see that the stock goes lower, you can buy more because then you are pretty sure that 66% of the time is going to rise the predicted value at least one time or more. So that's another thing good. And then the other one, it was mostly a qualitative analysis of the plot. So if it passes right through the middle of the stock, so that's going to be a good prediction. So like this one, so you see some part is up of the prediction and then some part is down, and it actually gets back to the line. So it's basically like oscillating. So that's going to be kind of like a neutral prediction. And for example, this one, so you predict a gain, but still you lose money here and then you lose money in all of this. So there's a bad prediction because you're basically losing. If you base your investments in this prediction, you're going to be losing money. So for this one, we get these results. Basically, we found that 44% were good prediction, which is really nice, and 24% were neutral. So this basically gives us 68% of relatively good, decent predictions, which will help us have a better understanding of the market, and then in theory we will get a little bit of profit from the investment. And also, I wanted to do, but what I think that in the future we can improve to basically not to have just a qualitative analysis, more a quantitative analysis. If can generate the linear regression of the stock, and then compare this with the prediction. So I think that will give us a better precision of how well is the prediction of the stock by estimating the correlation between the two lines. So yeah, so that's something that we can implement in the future. And these are the overall results, which is basically combining all the results. So we saw that the micro cap companies were the ones that we can predict the best, and the nano mark cap companies were the ones that we predict the worst. So that's also something to analyze, that maybe these ones doesn't have very high increments or lower increments, and then it is easier to predict than the ones that have lower capital and they are more volatile. So that's something to think about, and whenever we want to do a portfolio, a combination of investments, kind of consider to have more large-scale mid-capital investments than the others. So in conclusion, so like I explained before in the results, so we found some very good predictions. So it is still not very precise, but it is very hard to predict something randomly. And I consider that you can still get a little bit of profit if you base on this prediction, but there's still a lot of opportunity of improvement on this model. So has opportunity of improvement. So I was thinking in probably getting different predictions based in different size of the sampling. So probably we will get different lines to predict, or also changing the state of the system. So probably adding 7 states of the systems, or trying 3 states of the system, as well as modify them. So the most of the result will be in the middle state. So probably generating more states in the middle, and then in the upper or higher states. Also involves some external factors in the Markov change. So for example, I did this correlation analysis between 2 of the stocks, and I found that there's a 90% of correlation between this stock and this stock at a 3 days of span. So basically it's telling us that if stock 1 decrease, the stock 2 will increase the same amount, but 3 days after that one decrease. So basically, I'm thinking in creating one of these, creating kind of like combined state between the past value of the stock and then the current value of the stock. So maybe give us a better hint of the future of the stocks, of the stock price. So that's something to research in the future. That unfortunately for this project, there's not much time available to get to that implementation. And so I think that's all for my part. So I don't know if you have any question.
I believe there are tons of researches going on in the market price forecasting, right?
Yeah.
I think that's a good approach into it. And, you know, not sure how did you identify those independent variables? So you use some price, right?
Yeah.
Starting price and closing price, and but what about other factors like economic factors or?
So that's what I also want to try to do. So kind of also like I say combining stations. So also kind of like the inflation. So also the inflation will affect, and also the market if it is going, if there's a lot of sales in the market or lower in the market. So it depends.
It's really difficult to have a good prediction.
Yeah, and also to compute the states, so because you will have to manage a lot of information to get the probability. Yeah.
You know, a lot of people try to identify a good set of independent variable and then do some correlation studies. So identifying the key factors that might have an impact on the stock price changes, but still there are a lot of arguments there.
Yeah, yes, there's a lot.
Okay, thank you. Really an interesting project. Great job. Thank you. Thank you. Okay, so we have next presentation. Okay.
She's presenting the first section and presenting the second
Okay, so whoever want to present, use the mic. You can use that so they can hear.
Hello.
Okay.
Is it better?
Yeah,
Is
I
it
think
okay?
so. Yeah. Could you have a sec?
Yes. Thank you.
You know how to use that camera, right? Okay, just press the use.
So this and then
Okay.
okay.
Okay. Okay, you can grab a chair over there.
Sorry. Shit. I was like, okay, I can click it with this also, right? Here, next. Okay.
Yeah.
Great. All right.
Okay.
Thank you.
So I will hand it over to Sveta, next presenter. Okay.
Hello, good morning, everybody. So our team is, we are 3 people in the team, Mahmood, Ayat and myself, and we will be presenting Markov chain class project today. Before we dive into our project, I would like to give you a brief introduction of our Markov chain. So basically, the main goal of our project is to apply the class concept of Markov chains, what we have read so far in the semester. And we are doing a small 2 mini projects, and we are trying to implement that in our project. In the project, we will also calculate our transition matrix and the steady state cases as well. The next 20 minutes, we will be focusing on brief introduction of Markov chain, brief history, key properties, and a simple example, as well as Markov process. Then Mahmood will discuss our 2 projects, followed by conclusions on that. So we all know that Markov chain is basically named after a Russian mathematician who was in 20th century, Andrei Markov. His earlier works were particularly in the fields of algebraic and fractions, continued fractions and probability theory, but later on he was interested in the law of large numbers, and that eventually led him to develop Markov chains. So basically we all know, as per Markov chain properties, it is basically the probabilistic transition made from state to state, and the future depend on the present state. So it has the memoryless property, so it doesn't depend on the past state. So we can say that when we are doing Markov chain, we are assuming that it depends on fixed set of states, and there is a fixed transition probability, and it goes from one state to another, and that helps us to determine the transition probability matrix as well. So we can say that it is made up of a state space, transition matrix, an initial state. So these three constitute the Markov chain model. Any questions so far? Okay, so this is very useful process because we can determine the evolution of the process over time using Markov chain, right? So what happens in the long run will be completely determined depending on the transition probability which we will generate using Markov chain process. Here is a brief simple example which we have seen in the class so far. Suppose we say that it's raining today, and we say a second state like it's not raining today. So the probability of it's raining today depends on like 40% it will rain tomorrow if it is raining today. So if it is raining today, then there is a 40% chance that it will rain tomorrow, and there is a 60% chance that it will not rain tomorrow. And if it is not raining today, there is 20% chance that it will rain tomorrow, and 80% chance that it will be not raining tomorrow. So we can write it as follows. So if it is raining today, there is a 60% probability that it will not rain tomorrow. You can see it's t+1, so it's the next day. And this is a finite state diagram. So basically, it's a transition matrix, the transition diagram here. If it is raining today, then there is a 40% probability that it's going to rain tomorrow, and then there is a 60% probability that it's not going to rain tomorrow. And the same thing, if it is not raining today, then there is a 20% probability that it will rain tomorrow, and there is a 80% probability that it will not rain tomorrow. Okay? So let me not delete that. Let me not erase that. Okay, so you can see the transition probability matrix here. So if it is raining today, then we can write like, this is like raining today, it is raining tomorrow, not raining today, not raining tomorrow. So based on this transition finite state matrix, we can calculate the transition matrix, and the sum of the rows is always equal to 1. Stochastic matrix, the sum of the rows is always equal to 1. So using this example, we can find out the probability, like if we want to know the probability if it is going to rain after 3 days, if it is not going to rain, or it's going to rain after 3 days from now, depending on if it is raining today. So for our question, we have taken the example, right, that if it is raining today, what is the probability that it will not rain 3 days from today? So simply we have multiplied the probability, the transition matrix here twice. It will give us the probability of rain and no rain. So you can see after 3 days, it's not raining, the probability is 74%, right? Any questions there? This is the way we calculate the probability transition matrix. Basically, it's raining today, not raining today, and it is raining tomorrow, not raining tomorrow. So we get it like 74%, it's not gonna rain tomorrow. This is a simple example which we have already seen in our class. So this is very useful for determining the real life situations, which Mahmood is gonna focus on from now on, and we have used this method in order to determine our project in the class here. So I'll give it to Mahmood. Thank you.
Thank you. Just to summarize what Sridhar said about Markov chain, concepts that it describes the behavior or probability of a system as it moves from one state to another. So what is that? How does that apply to our first project? Well, our first project is about brand loyalty market share. And I will demonstrate how it applies to our first project. So basically there's a vendor, a new vendor that wants to know what product to carry, whether between Coke and Dr. Pepper on NMSU campus. And they want to know, as far as market share, what will be, who will have the popularity of these two products in any given week. So why is this important to the vendor? Because they want to do a revenue generation. And to us, it's important to us because we apply the concept that we learn in class into this first project. So to continue with our first project, and the assumption we made is that Coke and Dr. Pepper soft drinks are the only beverages at an MSU campus. Those are the assumptions that we made. And also the current market share for these two are 61% Coke and Dr. Pepper 39%. And the questions that some of the questions we want to answer is what happens after 3 weeks, and also long run, 20 weeks or 50 weeks or even 10 years. What happens? And does the probability of influence do starting probability influence in the long run? We'll try to answer these questions as we move on into this project. And so we didn't have data, so we had to do a little survey. And we did 125 students working around campus, particularly one main building, but asking, hey, which product would you like, or would you prefer between these two, and then after a week, would you still stick with the same product? And then we calculated that here in this Excel sheet. And from there, we had enough sample for this small project to build a market chain model. So we had to define the state of the system, and in this diagram, basically what this is that, as you can see, let me see. This here means that 80%, the probability of a student staying with a Coke is 80% in that week, and then the probability of students leaving after the week is 20%, going to a Dr. Pepper. And the same here, 60% will prefer with Dr. Pepper, and then 40% is just leaving to go into a Coke. So after this, we built our transition matrix, and basically first we wanted to find out for 1 week what happens after 1 week. And as you can see, we started with these first assumption initial state, and we ended up with a final state here after a week. This would have, as you can see, Coke popularity went up as far as market share, and then Dr. Pepper 36. And then what happens after 2 weeks? Right? We calculated that, and then the results, as you can see, is in the final stage here after 2 weeks. So we wanted to know what would be a steady state at some point where the system doesn't change anymore, right? And so we try to do that after third week here. We calculate our steady state here using this formula, and basically our initial state vector times the transition matrix to the power of m. M is number of weeks from now, and then you end up with a state probability after the mth week. So here we reached our steady state third week. Normally this takes a long time, 10 years or 20 years, but since this was a small project, we reached our steady state of third week. So we wanted to know, just to show the audience that, okay, what happens after 20 week then? And after 20 weeks, as you can see, the results are the same, right? Even 50 weeks, the results are the same. So that means we are at a stage where the results doesn't change anymore. And what does that tell us? Well, and based on our calculation here, this indicates that Coke has a better popularity than Dr. Pepper as our market share goes. And but there are some limitations to our study, right? That first we did only 125 students as a survey, and NMSU has a student population of in the thousands. That was one important note to mention here. And also, the areas that we took the sample was corporate center. And in this area, the student demographic is mostly undergrad. And so that creates some bias of our case study here. And another consideration, we didn't calculate this in our system, but we thought about as far as the experience of a student. Is it directly related to, is it based on the messaging, the commercials that students see, or it's direct actually taste that they like? And that's something, and then to address these limitations, I think further study could be done in the future to put include pretty much a whole NMSU campus rather than just one building. But we did this to demonstrate the Markov chain model. And that concludes our first project. And our second project, it's about bank loan portfolio. And generally, at a bank loan portfolio consists of three main categories, business categories. You have your retail banking, you have your business banking, and then also corporate banking. And in each of these, you have in the retail, you have basically an emphasis on individual customer loans, such as housing loan, business or small business, education, and we're all familiar with education with students here, education loans, and also miscellaneous loans, like personal loans, etc. And the next one is the business banking is emphasized on mid-sized companies, and they also do financial trading on related financial instruments to their business. And then last but not least is corporate banking, and they serve the top-tier corporate sector. And so we were given the current market share of these three different sectors. One is 39% for retail banking, 28% for business banking, and then 33% for corporate banking. So our research was about trying to find out basically calculate transition matrix to between four different, to calculate the transition matrix in retail banking. And with the retail banking, as I mentioned previously, it has a housing loan, business loan, education loan, and other loans. So why do we pick a retail banking? Well, first, it was retail banking normally has a greater portfolio compared to other loan portfolios, and also the second was the commodities in the loan is generally more popular in local banks, and that was another reason. And so why is this doing this transition matrix important? Because one, it provides the bank with the probability of loan allocation, right? Switching from or what are the probability of a loan switch, individual switching from one loan type to another. And hopefully that's what we're going to demonstrate in the next few slides. And so we needed data, right? You can't do anything without data and Markov chain. So we need the data. And we have our data here. It gives you the four different types of loan. And each one has the actual loan and also the proportions, right? And the proportion is basically you take this divided by this gives you that proportion. And from this data, we were able to construct our Markov chain model. And so the probability of a loan switching from type I loan to type J represented the following formula. Right? And I refers to the number of loan types. So the stage of the system here is defined using 4 types of loan for a period of 12 months. Within 1 year, so what happens, what are the probability that a house loan will, individual house loan will switch to a business or vice versa. So we have, we define a state of system here as you can see, an individual in the house loan, the probability that they stay in there is about 46.5%. Now, what happens if that individual decides to go from there to a business loan? The probability, within 1 year, the probability of that, in that period of 1 year, the probability is 13.1%. Right? There's another, I will talk about that at the end, but just to bring your attention here. If you look at business loan, probability of someone staying business loan is 26%, right? But leaving it, someone leaving is only going to this where other loans, which is about 73.6%. What does this mean? I will explain what this means at the end, but just to keep in mind that. So we were able to construct our transition matrix here, and basically coming from state I going to state J, we were able to calculate our probability matrix. And from there, we wanted to see what will happen in the long run and our steady state, and we were able to calculate that here, and we'll explain with these numbers at the end. Just when we use this pretty much general formula here. So our second project concludes that it's possible to switch from one loan from one type of individual to switch from one type loan to another. Right? And these are steady state distribution of loan portfolio shows that the optimal mix of the numbers that we previous slide were 32% housing, business loan 20%, education loan is 19.7, and other is at 28.3. And I mentioned earlier that people are going from business, only switching it from business to other is 76%, state is only 26%. And that is another observation we made, the probability. And at this, we concluded that the bank is not utilizing the business loan enough. Right? But this is enough. The reason, we don't know the reason, so we think that there's more research needs to be done of the reasons why people are leaving from business going to other, but not much the other way around. And that concludes our second project. And at this point, I'll open up any questions you guys have. Yeah.
Thank you. So I hope you guys enjoy the project. Okay. And by implementing what you've learned from class to real world problem, although it's very simple, but you have better idea how this works, right? Right. Okay. 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 Thank you, everybody, for providing the presentation today. Okay, so this is all for today. And next week, we're going to go back to the regular class. But this time, I'm going to introduce queuing theory, okay, to everyone. See you next time. Thank you. Bye-bye.